since this is just 1, which I think is a perfectly well argued back there, the average of a probability distribution can simply be found by taking each data point times how frequently it occurs and then adding them all together. Each data point times its frequency of occurrence, probability that is, add them all together. Add them all together. Let's do it. Let's actually do it with a single die. Now, we're not going to do this very often because it does get annoying when you get too many distributions. I mean, if you look at Gallup poll with 1,000 people, you don't want to be adding 1,001 things. You want to just, but let's see it. Let's see it, right? So for experiment number 1, the average number of pips, the first data point was 1. That happens 1/6 of the time. Is that fair? That happens 1/6 at a time. Ooh, lost the phone. There we go. Lost the phone and put a bunch of zeros in there. And lots of U's. But I think we got the point. We got the point was that. Then, add to it some. The next data point was 2, which happens 1/6 at a time. You see the pattern? Well, keep going.
Yeah.
3. Yes, I'm going to move this up here. Plus 3, which happens 1/6 at a time.
And then would you go 4, 5, 6?
All the way till you're done. All the way till you're done, Ryan.
To make the math easier,
Yes,
can you pull out 1/6 and multiply it by the sum of the?
happily. I'm not going to for a pedagogical reason. Do you hear what Carly just said? To make the math easier rule, why don't we just pull the 1/6 out, add up the 1 through 6, and then divide by 6? Totally.
You can't do it every time.
You can,
The
well,
probabilities won't always be the same.
correct. In any uniform distribution, it'll work, work beautifully. But yeah, in this one you can do it, but here's why I don't want to do it. I want to analyze each one of those pieces. I want to analyze each one of those pieces. This little piece right here, this is the only time I'll get this uber analytical about this calculation, just so you know. I mean, in general, I don't, but when you're looking back at what an average is, we very rarely get to the level of detail like we did on that first couple days when I gave you all lollipops. That was the last time we've ever analyzed that much of an average. I want to analyze this again, though. What is this piece doing for the average? What is that little chunk right there doing for the average? What do you think it's doing? Let me hear some ideas. What do you think it's doing for the average? What's that contributing?
Percent.
It's contributing, can I change percent to amount? It's the amount of the average contributed by
Ones.
the ones. That's the amount of the average contributed by the ones. 1/6 of the time you get ones. So this, over time, is the amount of the average contributed by the number 1 when you see it. Exactly, it's a little heady. So this is the contribution to the average by the ones that you see over time. You're going to see it 1/6 at a time. So 1/6 of that 1 is going to go to the average. 1/6 of that 1 is going to go to the average. What's this right here?
2.
That's the contribution given by the 2's. This is the contribution by the 2's. What's this right here? That's the contribution by the 3's. Exactly. This is the contribution by the 4's. This is the contribution by the 5's. And this is the contribution by the 6's. So each of those little pieces is contributing to the overall average of the distribution. Each little piece, each little tiny piece is contributing a little tiny bit towards the, and I say a little tiny bit, this is obviously much larger than that contribution because it's worth more, it's worth 6, where that one's only worth 1, but it's all got to give a piece. Go ahead, Pat.
But it's going to be the same
What's going to be the same?
over time. It's always
What's going to be the same? Define that. What are you saying? It's going to be the same.
that little contribution over time is going to be the same.
But not across each piece. Yes, you're right. The contribution averages over time to it, but each piece contributes a slightly different amount. Look, check it out. I like what you're saying. Hold that thought. This over time, I'm going to continue this on the side board. I don't think you can see that though. Let me tilt. There we go. Continue this onto the side board. We're still doing the average. I like what you're saying, Pat. But you gotta remember, the average is going to be the same, but the contribution elements are different because of the values of the variable. So the ones only contribute 1/6 toward the average
Right.
over time. The twos only contribute 1/3 toward the average, right? 2/6, 1/3. So they contribute twice as much toward the average. The threes contribute 3 times as much as the ones, which would be the half, yes?
Yeah.
All I'm doing is multiplying these guys out now.
Right.
I'm skipping the distribution step, which I think was a great idea, Carly, but this shows us how much or little each piece is contributing. The 4s contribute 2/3 towards the average. The 5s contribute 1/6 or 5/6 towards the average, and the 6s contribute 1. Now, Pat, when you said it's all going to be the same, what you mean by that is it all adds up to 3.5. That stays
Yes.
constant, yes. But the individual components are working their own. They're working the same frequency, but the amounts contributed each time are different. This is why Vegas works. The amounts that come out every time you pull that one-arm bandit vary widely from pool to pool, but the average stays constant underneath the pools. I like what you're saying, but you're looking at a more meta picture, or I'm looking at a more micro picture. You're going straight to this and saying it's 3.5 over time, and I'm saying, hell yeah, it is, you're right. But why is it 3.5? Because all these little individual pieces are playing together to make that 3.5. Does that make sense?
Yeah.
I love what you're saying. What you're saying is 100% correct, of course. Carly, go.
Well, I just have a question.
Yes.
I have a problem with these numbers.
Oh, okay.
We're working with a dice.
Yes,
dice,
you are.
that has on the dice, 1 and 6 have no, 6 has no greater value. I mean, essentially, we could have a dice with 6 different colors on
You
it.
could, and then you can't average colors, can you?
No. So why is 6 worth more than 1?
Because it's a number. It actually does have a numerical value on this die. It's the same thing as if you had 6 ping pong balls in one of those vacuum cleaner things for the lottery uses. You could put colors on those too, but then you can't average the colors. You could talk about the modal color, and then you could say, well, they're all having the same frequency. It's because you could also put different numbers on the dice. Instead of 1 through 6, put 2 through 12. Then the average would be 7, wouldn't it?
Yeah, but
Your choice, but you have to identify your values first. It's just like when you play in Vegas. The sides of the die, let's make up a game. Craps, you ready? Craps. The sides of the die are lose your dollar or win 2 to 1, which means win $1 back. Those are your 2 outcomes, correct? Those 2 outcomes could easily be lose your dollar or win $2 back because they double the payouts. It's all how you've defined your random variable. I'm not saying you have to define it this way every time. I'm saying this is how a die is defined. Your choice on how you define it. This is how Vegas takes your money. They define it in a very appealing sounding way, but on average it works against you more than on Tuesday. Is that a fair answer? I understand what you're saying. You don't I'm forcing the idea of a distribution to this die. We'll change it up and change the context soon, I promise.
Okay.
I mean, this is just this is my simplest example of a purely random distribution we can actually analyze.
Well, yeah, I mean, I understand it mathematically. And
Good!
it
Then don't get
makes
too
sense.
worked up about it. I mean, do, but don't get upset about it.
Yeah.
Because it's just by definition, I know how this is going to come out.
Well, I'm just wondering if there's ever any way to give those numbers the same value and still find the same, have each
Hold that.
number
Give
work the
me
same.
about 120 hours.
Okay.
That's the beauty of it. You want to be an actuary. You should be an actuary, by the way. You want to be an actuary. You want to set the rates, essentially, to have a certain result come out. Good for you. That's exactly what we're going to be doing by Tuesday. I love that idea. Hold that thought. 120 hours, ish, plus or minus.
But if you have 6, okay, you have 6 things on a dice, right?
You do.
Okay, so 1, 2, 3, 4, 5, 6.
Sure, why not?
The average is going to be 3.5.
Of course.
So you're throwing numbers in there, and okay, multiplying by 1, 6. But what if those numbers weren't 1 through 6? What if they were 3 or 17 or 42 or
Hang on, slow down.
88?
Hang on. Give me 3, 17, 42,
88.
88, negative 12,
Yeah, and
0.
yeah.
Recalculate it. The same logic. This won't be 3.5 anymore. It will be whatever that works out to be mathematically.
Okay, so it has nothing to do with the number of.
Your choice as to what goes on. Has anybody ever stopped to wonder why is it 1 through 6 on a die? No, because we've just dealt with dice all our lives.
Right.
The important part about the die isn't what's on the face. It's how likely it comes up. That's the important part. You can average anything you want. You can make half the numbers negative, half the numbers positive.
Right.
And it might average to 0. It might average to slightly less than 0. Your choice. This goes back to Carly's point.
So the 3.5 isn't.
Is a consequence of 1 through 6.
That's what I'm.
Yeah, but you can make it be anything you want. That's what Carly's saying. We can make that 3.5 be a negative 10 if we arrange the numbers right. Totally. And this is part of what being an actuary is all about. Let's make the premium be a negative 200 on average, so our company can stay afloat. You're adjusting the size of the die. You can't adjust the probability. People are going to die at the same rates. But you can adjust the premium payments so that the average changes to a certain value over time. Don't get too hung up on the 1 through 6. That's just a consequence of the die. You can play with that all you want. We're going to start playing with it.
So the 3.5 has nothing to do with the 1 through 6 spaces on the die.
It has more to do with the 1/6 on. If you change these 1/6s to different numbers, you'll get a different average, won't you?
Right, because
Yes.
the numbers on the
Situation. I like that,
die.
Cassie.
That's why you can't put colors like.
You couldn't average colors.
Right.
Exactly, because they're not numerical. Cassidy said it's situational. Perfect. This is just one situation. There are many of them. Tell me what's on your mind. It's very
I think
patient.
the confusion is we're counting the pips, not the sides. So
How would you
I
count the
think-
sides?
Well, because we're talking about 1 through 6.
Yes.
We're not talking about the 6 sides. We're talking about
What's on the 6
pips
sides?
Yes.
On the sides.
Isn't
So
it
we're
easier to
counting
count the pips? Isn't it easier to count the pips and the sides? Because what would side 1 be?
How many sides versus we're not counting when you'll come up to a certain side. We're counting the actual pips.
I like that very
themselves.
much.
I think that's really confusing.
I like that very well. I would hope it would be less confusing than trying to count like where side 1 or side 2. I think when we put both dice together on Tuesday, that'll clear that confusion up. I think. I could be wrong about that, but I don't think I am. Alan, go ahead.
I was just gonna say, I think we're more, right now, I think the confusion is we're more concerned of the numerical value on the side of the dice rather than the probability of the dice.
Yeah, be focused on the fact they all happen 1/6 at a time. Keep that. That's kind of the big picture right now. You guys are getting very, very micro in the 1 through 3, 4, 5, 6. I mean, I could have just made that, like Carly said, be 7, negative 12, 0, whatever.
And that's where you could use the colors, because it's still the same probability.
Right, you just couldn't get a numerical average.
Right.
Or a standard deviation. Anybody pissed about the fact there's no standard deviation on that 1 bar stats?
It's not just because it's a uniform distribution.